Okay, so let me recall some notation. So let me fix G over F quasi-split, T in B in G, all the usual stuff, so I can talk about standard parabolics and standard levies. P mu is standard levy, standard parabolic. So recall from yesterday that we had these two functors, which will go from int_co of the parameter stack for the levy, between that and int_co of the parameter stack for G, and the one going this way is denoted is P spec, and the one going this way is denoted CT P spec. Right, so Lucas defined these, and these are an adjoint pair. This is is left adjoint to this CT. And it's clear from the definitions that this is has a good finiteness property. So is sends co-QC for the levy to co-QC for the whole group. It's not at all clear that this CT has any good finiteness properties. Okay? So it's defined as a pullback along some proper map, which is not a finite Tor dimension, and then push forward along a map that's not even proper. So usually this would ruin coherence, like very badly. And a priori, this does ruin coherence, but there's one little thing that we can do to fix it, it turns out. So now let me fix some chi. So this will be a character of the Galois invariant center, or Day invariant center of the dual levy. And so we'll define the chi part of this functor, so CTP spec chi. Let's go from int_co par G, unsurprising, int_co par M. And then we saw yesterday that the target here will have this grading by characters of the Galois invariant center, right? And so you can just project anything you want onto its sort of chi-graded part. So this is some, I'm having this problem too. This is some projection, and this is like int_co par M chi, okay? And so this is, of course, just CT. P spec. So this diagonal arrow is what we're interested in. Can everyone read that? Okay. I'm sorry my handwriting is so terrible. So theorem. So this is the key application of sort of all the stuff we saw yesterday. So first, this functor, CTP spec chi, this preserves co-QC. So these are the compact objects in int_co in this situation. So this is saying that this right adjoint has this kind of miraculous property that if you project to one sort of chi-graded piece, it actually preserves compact objects, okay? And there will be a part two, so for F in co-QC of the levy, some fixed sheaf. Ignore these random dots, I'm not going to bother erasing them. CTP spec chi F. This is 0 for all but finitely many P dominant chi. Okay? So you have to read this carefully. I'm only making a claim about P dominant chi. Okay, it's easy to write down F where this is non-zero for every chi which is not P dominant, but for some reason this is true. Yes, yes, sorry, that's a typo. Thanks. Okay, any other questions about this statement? Okay. So sketch. So the first ingredient is a really important result, which we'll use several times today, actually. This is this Nice result was proved by Yuta Takaya, who's sitting somewhere in here. And so this says that co-QC of the parameter stack for G, so this is generated under finite co-limits and retracts by sheaves of a very special flavor, so namely sheaves of the form I's P, I want to do P prime spec. F prime. So here P prime is a standard parabolic. Let me make this more legible. That didn't work. Made it worse. P prime is standard. And F prime, you can impose very strong assumptions. So in fact, this will be a perfect complex quasi-compact support, and it won't live randomly on this parameter stack. It'll live on the locus of supercuspidal or irreducible, if you prefer, parameters. Okay, and this was proved by Takaya. And I'll put an exclamation point because this is super useful. Okay, and so we've harped a bit already on the difference between QCO and INTCO. This is kind of the subtlety we're trying to overcome, improving categorical Langlands. This tells you that if you have a handle on kind of QCO for levies, and you know how to think about parabolic induction, then you might have a chance, right, of understanding QCO of the whole thing. So this is some kind of quantitative version of that. Okay? So what does that do for us? That means that in the thing I'm trying to prove, F was a random coherent sheaf on the parameter stack for G. But all the statements I'm trying to prove are stable under kind of finite cones and retracts or whatever. So now I can just assume F is of this form. Okay? So thus can assume. So thus, it's enough to show same claims for CTP spec chi of I's P prime spec F prime in this notation. Okay? And you'll remember this kind of composition. I'm sorry, my handwriting is truly dreadful. It makes me want to vomit, but I guess we have to live with it. So yesterday, she started with an I's and then composed it with a CT. This is exactly what Lucas was calling F, and this is what the spectral geometric lemma lets you decompose, right? And so this is, in fact, what you would notate as F chi in yesterday's notation. Okay? Jared, you look unhappy.
I can't read the sentence. Thus.
Enough to show, same claims.
Oh, enough to show.
Sorry. I can barely read it myself. Okay. And so now, you may not be surprised that the next step is to apply this spectral geometric lemma, which I denote like this, with P1 being the thing we're inducing along, so P1 has to be P prime, and then P2 is the thing that we're doing constant term along, so P2 has to be P, right? And that will decompose this F chi up to some filtration into these pieces indexed by Weil double cosets of some F chi W, and then recall from yesterday, each of these F chi W's will in turn have its own n-index filtration. I'll get to that in a second. And let me recall also a piece of this horrible giant diagram that you saw yesterday. So if you fix a Weil group element, then you have a diagram.
What's the notation in front of the
Equals. I put equals with a superscript graded. So the left-hand side has a filtration whose graded pieces are the right. Yeah, it's just some heuristic notation. Okay? Maybe this. I put it over the equals sign. Yeah, yeah. Up to graded this equals this. Is that better? Okay. And so let me recall a little bit about the geometry that you need to make sense of these symbols F, W, chi, because there's a really important observation that will come along in a second. So here I had this parameter stack for the thing I'm inducing from, so this would be M prime. And then in the notation yesterday, we had par Q1 goes down to some par L1, which is secretly some par L2. And then this goes up to some par Q2. This goes to par M. Right? And then there was some more stuff up here. I'm not going to write all of it, but this should look familiar from yesterday. Right? And the important thing to notice here is that Q1 is a levy in M primed. Sorry, parabolic in M primed. Okay? Now let's go back to the sheaf that I was feeding in. So this theorem of Takaya says I can take I spec of something that lives on the supercuspidal locus of this levy M primed, right? So that immediately tells you that if Q1 is a proper parabolic in M primed, when you pull along the very first arrow here, oh, I have this laser, don't I? When you pull along the very first arrow here, you're going to get 0, right? And then you're done. So the only W's that contribute, this gets a double exclamation, so the only W contributing are the ones where Q1, which is a priori a parabolic in M prime, is all of M prime. So Q1 actually equals M primed. And then in this case, because it's a parabolic with levy L1, this means it also equals L1. And then if you squint, you're going to see that life is going to keep getting better and better, right? Because this diamond that I didn't draw all of here, let me use my laser gun again. This diamond here is Cartesian, right? So if one of the legs is an isomorphism, so is the other leg, right? So this horrible diagram is going to collapse a bit for these W's. And so for these W's, which are somehow the only relevant ones in the diagram, collapses a bit, let's say, to par M primed. This has a map down to it from, I need more space. It collapsed, but it didn't collapse that much. Primed, this is a map down to it from, sorry? So we're trying to do constant term along a fixed thing P, and we're using the fact that all the sheaves we care about can be generated by I's of some other levies, other parabolics P prime. And so you should think that P prime is kind of a random auxiliary parabolic. Okay? And so we're inducing from P prime and then restricting along P. Okay? And so then this turns out to be this group K, W, and then up to some Weil twist. This is the same as the parameter stack for Q2. And so Q2 is still a levy in M, and then you just get this. This is par M, and then here you have this map. I think this was HW yesterday. Here you have par HW. And this I want to call FW, and this I want to call GW. Okay? So this is some piece of the diagram from yesterday. Same notation. And what's important to note here is that FW is actually proper. FW is mapped from the parameter stack of a parabolic of M to the parameter stack for M, okay? And so you can start to see now why this is going to work. Push forward along FW is proper, so it's going to preserve coherence, okay? And then pull back along GW, we're feeding in something that's perfect, because F primed is a perfect sheaf on the parameter stack for M prime. And so then the only question is kind of what happens in the middle. So from yesterday, so you get this FW chi, again up to grading. I hope this notation is okay now. It'll be this big direct sum over N, FW chi N. And what is this piece going to be of F? And this will be FW lower shriek of, let me just write some things and then I'll say some comforting words. This is a finite set with some characters. This is the same sheaf that Lucas wrote down yesterday. So these symmetric powers of normal bundles all the way up top pushed along this map HW gives you some weird kernel sheaves on par KW. And then to be careful, you have to sort of push them along this Weil twist, but don't worry about that. The chi should be outside it. And that should be that minus that. And then what do I tensor this with? I tensor this with GW, sorry. One more time. Two more times. So I had this perfect sheaf f primed on the Levy stack. It's on the parameter stack for m primed. So I can pull it back along GW and then just push it along this isomorphism. And because this is a perfect complex now on the parameter stack for Q2, if you stare at where things live, it will have a central grading of its own, and only finitely many of those terms will be non-zero. So these x's run over the non-trivial characters for the central grading of this pullback thing that's appearing in the second slot here, okay? And that's a finite set. And so now what are the key points that make us basically finished? So this is perfect. And so now observe. So one, because what's our goal after all? Our goal is to show that this f chi of curly f prime is coherent, right? This grading by w's is a finite filtration, so we can show it for each fw chi. This is an n-index filtration, right? So we better be pretty careful about this step. The only way that this is going to help us prove coherence is if all but finitely many terms on the right are just zero, right? Unfortunately, that's true. So for all but finitely many chi w lower star GW and chi minus this is 0. Wait, sorry, all but finitely many n, excuse me. Chi and w are fixed the whole time. So as n goes to infinity, sort of the weights of this sheaf are disjoint from any fixed set of characters, okay? And chi is fixed, and xc runs over a finite set. Okay, so only finitely many n's contribute to this filtration, so that's really good. Also, Lucas stated yesterday that exactly in this situation where one of the two QIs was the whole MI, these are all perfect. This is perfect, as we saw yesterday. And now we're in pretty good shape, right? Because, let me get my ray gun out again. This is perfect. This is perfect. Tensor product is still perfect, right? And what's left? The only thing that's left is this. This is a proper map, and push forward along proper maps preserves coherence. It's proper. So FW preserves co-QC. Okay, and that's the proof of part 1 that CT chi-graded summon preserves co-QC. Okay, so we use the full power of this lemma, at least in this special case where one of the QIs is MI. Questions about that sketch of that part of this theorem?
Can you explain again why only such W attributes?
Yeah, absolutely. I mean, that's a key point here. And the point is that I'm replacing my random sheaf that I'm feeding into CTP chi with a sheaf of this form, which I hope is somewhat legible from context. So this is some spectral eyes of something that lives on the supercuspidal locus for the Levy M primed, okay? Now when I go to this diagram, here Q1 is a parabolic in M primed. So if Q1 is a proper parabolic, the image of this map will be disjoint from the support of F primed. And therefore, everything will collapse to 0. So the only W's that contribute are the ones where this is an isomorphism, and that's just the same as Q1 being M primed. Okay? Yeah, this is the key trick that makes this work, is that you can generate stuff using stuff on perfect complexes on supercuspidal loci for levies. Okay?
What is the supercuspidality assumption in Takay's theorem? The generating set, they were perfect. Is that what IRED means?
IRED means the open-closed locus of supercuspidal parameters.
Thanks.
Yeah, which in this L-adically continuous context is the same as saying irreducible. Other questions? Okay, that was the sketch actually of 1, and for 2, you just need one more detail. So this gives 1. Yeah, wrong. I don't want my ray gun anymore. And for 2, you need quantitative vanishing results. for these W lower star G, W, N chi's, because now we're trying to make a kind of even stronger claim, right? That if curly F is fixed, but now I'm allowing chi to vary in the dominant region, I want every single term on the right-hand side here to be 0, okay? And you can do this, and I don't want to say exactly what the combinatorics are, but if you really want to know, this is remark. The exact result you need is remark 3.6.4.3 in the paper, okay? So that's all I want to say about that. Okay, questions about this? This is our main application of this whole spectral geometric lemma story. Okay, this is the end of the spinach. All right, so corollary 1.
Sorry,
Yeah.
just want to maybe clarify the statement of 2. So do you mean that it's non-zero only for finite many dominant ones, or you only know this among the dominant ones?
If you restrict to dominant chi, it can only be non-zero for finitely many of those.
Right.
For non-dominant chi, you have no control, and you expect it to be non-zero infinitely often there. Yeah.
And you're basically saying that's the only obstruction for.
These two statements are complementary somehow, right? For any chi, this thing preserves co-QC, and if I feed in a fixed co-QC, then at least in this cone of dominant chi's, it's almost always 0. Okay? And by the way, 1 here you can prove, I think along the lines Xinwen hinted yesterday, where you somehow do a reduction to tame and then go to ISOC and then actually translate this into some theorem of Bernstein or something, but I don't know about 2. Some of these corollaries have a similar chance of being proved by tricks like that. Okay, so consequences, if I can spell it. So the first is this theorem that was already stated yesterday. So this is for all F and G, co-QC, RG. This Arham FG, so this is a bounded complex of cohomologies, finitely generated as modules over the spectral Bernstein center. Okay? And so this we've seen in several different incarnations. You can think of this as global functions on par G. I like to think of it more as global functions on the coarse quotient of par G, which we notate xg spec, okay? And again, this is not obvious at all. This stack has singularities. There's no reason that Arham of coherent sheaves in a singular situation should be bounded. It would be false if it were a variety, okay? So morally, the stackiness and the singularities are playing against each other for this to have a chance of being true, okay? But the proof is actually kind of easy with what we did so far. So proof. So again, we're going to use Takaya's result. So without loss of generality, F is some I's P spec of some, oh, I used letter G already. That's a bad idea. Very bad idea. F primed. So P a parabolic. And F primed. I can put the strongest assumptions that I had as before. I can even assume this is in perf QC of the parameter stack for the levy of P. Okay? Because again, up to finite colimits and retracts, I can just manipulate F however I want, right? So F will be obtained from things like this in finitely many steps. And I can even assume F primed is graded for a single chi, because any F primed will be graded for finitely many chi, so just pass to the finitely many chi where it's non-zero, okay? And then, let's just think for a minute, Arham F to G. Well, F is a spectral I's, and so constant term is right adjoint. And so this is the same as Arham F primed. And I could put all of CT spec, right, but F primed was chi-graded, so I can even put the chi-graded part. And then what do you know? So this is perfect. And this is coherent. And if you arham from a perfect thing to a coherent thing, you get something bounded. Just always. Okay? And the other statements I'll sketch also because they're pleasant. So for the other claim, this finite generation, look at this map, which maybe you haven't used much, but will come many times. So this is the map from the parameter stack to its coarse moduli space, which I like to notate xg spec. So this is the coarse moduli map. Okay, and we've already seen that this xg spec is extremely nice. It's a disjoint union of affine varieties, right? In fact, it's a disjoint union of tori modulo finite groups of automorphisms, so it's Cohen-Macaulay. It's really great. It has kind of only the defect of having infinitely many connected components, but other than that, it's beautiful, okay? And so then, let's think about what this is. So this arham fg. Well, how could I compute this? This is global sections of internal arham upstairs. I may as well then push that downstairs and take global sections downstairs. So this is r gamma on xg spec of internal hum, let's say q lower star, internal hum fg, okay? And now what do you know about this? So this is a priori just a bounded below complex of coherent sheaves, right, upstairs. But at least it has coherent cohomologies. And this Q, in the old days, we would say that this is the GIT map of par G, but nowadays we have a slightly cooler term. We say this is a good moduli space in the sense of Alper. And one property of good moduli spaces is that push forward along such a map is exact and preserves coherence. So when you do this push forward, you'll get a bounded below complex of coherent sheaves on this xg spec. And because f and g had quasi-compact support, this will clearly have quasi-compact support, so it'll just live on finitely many components downstairs. And finally, each of these components is affine. So what's r gamma going to do? Well, it's just taking global sections. And so this is a disjoint union of affines. And so if you put all these things together, you immediately see that the cohomology in each degree is finitely generated over global functions on this coarse moduli. And that's exactly what I was claiming, right? So note in this step, you don't get boundedness, right? Because this, I just want to highlight this. So this complex is genuinely unbounded to the right for most examples you care about. But by some miracle, when you push and take global sections, you kill some tail that drifts off to infinity. Okay? Questions about this?
What is the difference? Previously it was bounded, but then now...
Oh, maybe this should have like an underline, its internal hum. Yeah, the external total R hum is bounded. The internal one is wacky, okay? Yeah. Other questions? Okay, so I should just say as a preview of what's coming later, we're going to use the full power both of this whole theorem that I've stated here and this theorem, which was a corollary of it. And those will both be ingredients in the proof that R psi preserves compact objects. Okay, so we need all of this for that, which will happen in lecture 4 tomorrow. Okay? I wanted to do some more consequences of this. So yesterday, Lucas alluded to this notion of admissible sheaves. And you may have seen this notation where we somehow intersected admissible with co-QC, and this got some other name. I want to talk about this story now. Okay, so now admissible sheaves. So definition, so if X is a disjoint union of QCA stacks, don't worry about this general gobbledygook, just think it's par G, okay? So here's the definition. F in int co of X is admissible? Well, there's several ways to think about it. So Xinwen has a very general, pleasant, abstract way of thinking about this that works in any dualizable category. And here INCO is not just dualizable, but in fact compactly generated. So you can specialize that formalism to this. It also turns out that these are the suave objects in the INCO six-functor formalism. But I prefer the absolute most down-to-earth way to think about it. And so that condition is that for all G in co-QC of X, this total external Arham from G to F is a perfect complex of vector spaces over my base field, which is always QL bar. Okay? So external Arham from co-QC gives you something extremely small, is the condition. Okay? But these can still be quite large. Okay? So if X is the classifying stack of some reductive group G, I invite you to convince yourself that the regular representation of G, so the coordinate ring, regarded as a G representation, that's admissible. It's certainly not coherent. Okay? So these can be large. In some sense. And of course, we have some notation for this. So we call this, I'll notate this ADM of X. So this comes with a duality. Notated D admissible, characterized by the formula. This is going to look a little weird, but we'll probably see it in action later. So I want Arham from G to this to be Arham from the Grothendieck-Serre dual of G to F. And then I want to take naive dual, as a complex of vector spaces over my base field. Okay? So you can check that this formula actually does define some contravariant endofunctor on INDCO, just by using representability theorems in some way. And this D admissible is defined, and this is for all G. It's not a G, that's just a mess for all G. QC. So this endo functor makes sense on all of INDCO, and it turns out it's an involutive anti-equivalence from admissible sheaves to themselves. So this gives an involution on admissible sheaves. The admissible is an involution. Say involutive anti-equivalence. Okay, and this is cooked up, as we saw yesterday, this is somehow cooked up to match a Verdier duality on bun G. Okay? So theorem. And I guess I'll present this slightly differently than Lucas did, so the notation will be the same, but psychologically for me, the notation has different meaning. So if I take co-QC of the parameter stack, and I intersect it with the stuff that's admissible, so this is kind of imposing both finiteness conditions. What do I get? So this, I claim, is co-par G fin. So yesterday, this was the definition of the right-hand side. But for me, the right-hand side is a different definition. So where right-hand side is objects F in co QC par G, which are supported on finitely many closed fibers of this coarse moduli map from the parameter stack to its GIT quotient. By closed fiber, I mean fiber over a QL bar point. Okay, so really fiber over a closed point. So this is like asking, obviously an object of co-QC upstairs can have very, very large support relative to the base, right? Imagine like the structure sheaf of a component. Here we're cutting out a very thin subcategory, just the stuff that lives on finitely many fibers, right? So this is a small subcategory. And I claim these coincide. So if you want something to be in co-QC and admissible, it's the same as imposing this kind of down-to-earth condition. You have a question?
Yeah, sorry, I'm confused about what you mean leaving over finitely closed fibers. You mean like you take a finite set of closed points in the coarse moduli and pull that back?
Yeah, and it's set theoretically supported there.
Okay.
Yes, but any finite set will do. Yeah. Other questions? Yes, it just means fibers over closed points. Yeah, sorry. Fibers over closed points. Other questions? Okay. So let me give a little sketch. So what's obvious and what's not obvious? So obviously, the right-hand side is contained in CoQC, because if you live on finitely many fibers, you certainly have quasi-compact support. So first, you have to convince yourself that the left-hand side lies in the right-hand side. But this is fun. Why is this fun? Well, let's think about what happens if I take some element of the left-hand side. So this is in CoQC, and it's also admissible. Therefore, RHOM, what does it mean to be admissible? RHOM from anything in CoQC is a perfect complex. F is in CoQC, so RHOM from F to itself has to be a perfect complex of vector spaces. In particular, endomorphisms of F. This is an Artinian Bar algebra. And if you think about what this means relative to its support, right, the support of this sheaf will be sort of a closed subscheme cut out by this ring, if you like. And if this is Artinian, that means that it just has to live at finitely many of these fibers, okay? So the natural map from O of XG spec to endomorphisms of F, this factors through sort of O of a finite length closed subscheme. Of XG spec. And that will even give you the finitely many points that you need to take the preimage of, right, to get the fibers where this thing lives. Okay? And last, you have to convince yourself that the right-hand side lives in the left-hand side. So that just amounts to saying that you need to understand why something here is admissible. Okay? And so CoQC, sorry, Co. I'm going to stop writing parg everywhere. That's the only time I ever care about this subscript fin. And so now you have to compute RHOM from some G to F. So this is just a random thing in CoQC. And this is a random thing in CoFin. Well, what do you know about this? We know by the hard work we did already that they're both in CoQC, so it's bounded, right? And its cohomologies are finitely generated. Sorry, I wrote G is contained in CoQC, and F is contained in CoFin. CoFin contained in admissible, question mark? Yeah. This is all left to show, okay? So what do we have to check? We have to check that if I RHOM from CoQC to anything in CoFin, I get something bounded with cohomologies that are fine dimensional vector spaces, right? So this is bounded because we have this big sledgehammer from earlier, right? Any pair of things in CoQC, the external RHOM will be bounded. So you just have to see that now that in each degree it's a finitely generated vector space. But that's okay because the cohomologies are finitely generated as modules already over this O. Sorry, let me use my preferred notation again. This ZG spec. And finally, F has this property that endomorphisms of F are Artinian, right? Because remember, F lives on finitely many fibers by assumption. And so F is killed. And so it's killed in each degree by the kernel of ZG spec mapping to endomorphisms of F, and this cuts out, has Artinian quotient. Say I. Okay, so it's really quite naive, actually. You know, the cohomologies are finitely generated over this ZG spec, but they're also killed by some ideal of sort of finite co-length in ZG spec. So in fact, they're finitely generated as modules over an Artinian quotient. Artinian quotients are finite dimensional as vector spaces, so it's finite dimensional as a vector space. That's it. Okay? Questions? Okay, I want to now just state one more thing on the coherent side. Oh, actually, How many more things do I have? Let me do 2 more things on the coherent side. So now just suppose that x is par g, but I'll say out loud what conditions you need for this to be true. So if x is par g, and this thing I'm writing down will be used crucially in the 5th talk in the discussion of this functor t psi. Okay. Then for f in co par g fin, this admissible dual of f, which a priori is just some weird incoherent sheaf, okay? This actually lies in QCO, so we saw this yesterday. And you didn't lose any information by taking this dual, because if you take the dual again, you get back f. Okay, so this I don't really have time to sketch the proof of, but this will be used crucially in the 5th lecture. And actually we prove a much more general statement in the paper. It turns out that the admissible dual of anything in co gets sent into QCO, which is really strange, and I don't fully know why this is true. But there's a much, much weaker statement that suffices for what we're doing here, and this will be in like the notes that we write for the conference proceedings. So if this part of the paper is scary to you, there's a softer alternative, okay? And so proof, let's take omitted. So like 8 years ago when AI was really bad, I remember someone fed the Stacks project into a really bad AI and asked it to come up with more stuff. And it didn't really come up with any stuff, but it did learn that a valid way of proving something is just to write the word omitted. All right, so next, I want to change gears a little bit, although you'll see why it's not a huge change of gears. And I want to talk about a mechanism that will pass back and forth between kind of arbitrary objects in situations where you have an action of QCO par G, and objects that in some sense are spectrally decomposed along semi-simple parameters. So this will also be of crucial importance later. And the definition, again, will look a little bit funny. So I'm going to make a few definitions here, actually. So for any closed point in this course moduli, so you should think that I'm using this letter for a reason. So this is really a semi-simple L parameter. That's exactly what points of this thing are. I'm going to write O phi R-E-S-T-R, so that stands for restricted, okay? So let this be the local cohomology sheaf of O par G along the fiber Q inverse phi. Okay, so this looks terrible, but it's not, so explicitly. This thing downstairs up to component issues that you should ignore is affine, right? So this is just cut out by some ideal, F1 through Fn. Then this thing I'm defining, well, up to quasi-isomorphism or whatever, you can represent it as a complex that just looks like O par G, maps to direct sum I, O par G, convert each of them individually, maps to direct sum over I less than J, O par G, invert Fi Fj, and so on. So this is just the alternating check complex where I invert the Fi's, okay? And if you look at this complex, you notice the first term is O par G, and so the stupid truncation of this in degrees less than or equal to 0 is just O par G, and so you get a canonical map, which you can also think of much more conceptually from this. That's not what I want. This will come along in a second. O phi restricted O par G. There's a canonical map like this, and don't be scared, this map exhibits the source as an idempotent co-algebra object, right? So usually an algebra object would have a map from the structure sheaf that had some properties. Here you have a map to the structure sheaf that has some properties. And this has the funny property that if you tensor with itself, it's just the same as the thing you started with. So this is the sense in which this is idempotent, and you can convince yourself that it's a co-algebra in some way. And I'll just write these words because they're fun. And it makes me sound cool. And similarly, you can set O. Now there's no parameter subscript. So this will be the direct sum over all phi of these O phi restricted. By definition, this is just some huge quasi-coherent sheaf on the parameter stack for G. Okay, really, really huge, big infinite direct sum, uncountable direct sum, in fact. What?
What is this tensor over?
It's a direct sum.
Above it.
Over the structure sheaf.
It doesn't map.
It's an idempotent object. Really funny, but true.
It both receives a map and has a map towards.
It has a map towards the structure sheaf. If you tensor that map kind of with this O restricted, you get O restricted mapping isomorphically to itself, and various diagrams commute. Okay? So this is also of the same nature, because each of these things are, and it turns out if you tensor one for phi with another for a different phi, you get 0, so they don't talk to each other. And now here comes the key definition. So suppose given C, some object of PRL with an action of QCO par G, we set C restricted. So this is the full subcategory of objects A, such that the natural map, let's think about this for a second. Well, this whole QCO acts, so this O restricted will act on any A. This will give me some crazy object in my category. This thing still has a canonical idempotent coalgebra structure. You just direct sum all the given ones. And so there will be a canonical map from this to O par G acting on A. But this is the unit in the category that's acting, right? So this is just A. And the condition is that this map is an isomorphism. Okay? What? Full subcategory of A such that the natural map is an isomorphism. A in C. Sorry. Oh, that's truly bad. That's a C. Okay? And notice that by definition, this O restricted is this big direct sum, right? So if you have an object A, which lives in this restricted subcategory, then A is this, right? And this thing has this big decomposition, so then A gets a big decomposition too, right? So if A lives in C restricted, then there exists canonical decomposition A into some big direct sum over phi of pieces A phi, okay? So this passage from C to C restricted and back will be very important in the 5th lecture. Okay, so let me just make some comments out loud about formal properties that this has. So first of all, because I'm asking that some map involving a tensor product and then one arrow be an isomorphism, this will commute with all colimits, so this subcategory is stable under all colimits, okay? In particular, it'll have a right adjoint, which a priori doesn't usually have much nice structure, but often, and I'll say this in a second, so this, a priori this has a right adjoint, which could be terrible. But in practice, in all the cases we care about, the right adjoint is explicit, and it's actually given by sending some object in the ambient category. I may not use A, because I already used that for something that was restricted, by sending B to O restricted tensor B. So this is a funny thing. If you take a random thing and act on it by O restricted, you get a restricted thing. Because remember, O restricted tensor O restricted maps isomorphically to O restricted, right? So this tensoring by this giant monstrosity has the effect of shooting you into the restricted subcategory. And it turns out under some mild conditions, this is actually right adjoint to the naive inclusion, okay? And so now here comes a theorem. Because what good is all this if you can't say what this restricted thing is in practice? So first of all, we can take the universal case, right? Because here C was something with an action of QCO. Well, QCO of par G has an action of QCO of par G. So what is this? So this should be some subcategory of QCO par G. And it turns out that you can say exactly what this is. Up to int completion, it's the subcategory of perfect complexes with the same condition of being supported on finitely many fibers. Okay. And similarly, intco par G restricted. And sorry, I don't want to write equivalence here. I actually want to write equals, which usually is not a good idea with categories. But both of these are full subcategories of, in the first case, QCO of par G, and in the second case, INCO of par G. So I have a coincidence of full subcategories. So I think it's OK to just write an equal sign. So this is int of co par G. Okay, so if this fin thing looked really weird and ad hoc to you, this is another way to think of how it arises. It's somehow the stuff that is restricted in this abstract sense. It's the stuff that admits some kind of canonical direct sum decomposition indexed by semi-simple parameters. Okay? Questions about this formalism?
I guess there are different things that have been considered in the literature where you have a semi-simple parameter, so where you either localize around some maximum ideal in the excursion algebra, or you take some formal completion.
Yeah, so I mean, the one I wrote in that appendix of your paper with seeing is like too weak for most applications.
But this is like more like the localization.
Yeah, this is exactly the same as what Hansen and Xinwen consider in their paper.
So it's more like the formal completion.
But in the sort of co-free sense, not in the free sense, right? Because when you talk, okay, this is an issue that's already come up multiple times. Formal completions have sort of two different incarnations, right? If you have a ring and an ideal, then like derived I-complete things in the derived category are the same as I-torsion things by some non-trivial equivalence, right? And so one of them last week was going under the term free monodromic, and the other was co-free monodromic. This is more like the co-free story, okay? So you can hallucinate that there's some analogy with this and this co-free monodromic world, okay? Where instead of some local systems being the indexing set, you have all these var-phis. Okay, questions about this?
Well, can I trouble you to ask this OP restricted, well, could you say what universal property it has so I don't have to wonder why it's maybe canonical and doesn't depend on the Fs you chose?
I mean, that is the first sentence I wrote. It's the local cohomology.
Could you repeat the question?
Right.
Yeah, so I presented it in this way where I chose a bunch of Fs, right? What's a canonical way to think about it? A canonical way to think about it is that for a given var-phi, inside of QCO, you have the stuff that's supported set theoretically on the fiber, okay? That inclusion has a right adjoint for stupid reasons. You apply the right adjoint to the structure sheaf, and that's this O-phi restricted. That's all. But then as a human being, you want to know that you can write it down in some useful way, okay? And this thing I wrote maybe looks a little weird because I'm still inverting all these Fs, but you can think of this even more concretely as some co-limit of Koszul complexes, right, where I sort of dilate by higher and higher negative powers of the Fis. And that's actually how you prove this theorem. You just kind of play with the fact that this O restricted is a very concrete co-limit of Koszul complexes, and you win, okay? So I have not budgeted my time very smartly. See, I'm on page 3 of my notes. So in the last 5 minutes, let me do some quick, if I can spell it, promorphic recap. But I think it's OK that this is quick because we have seen a lot of this already in multiple lectures, in Ming's talks last week, in Paul's talks, and in the Q&As. But let me just go over this very, very briefly to fix notation. OK, so same as before. So we have D of bun G. This will always mean D least with QL bar coefficients. I'm not going to write that every time. So with its natural semi-orthogonal decomposition, we've also seen what this means. And it's compactly generated. And on compact objects, you have this very nice duality, this D, BZ, and then we also have ULA sheaves. And on this, we have this other duality, this Verdier duality. And then key thing that we're going to use a million times to get from one side to the other is this theorem of Farag-Schulze, which we've already seen, but I state it one more time. So there is a natural action of Q par G on D bun G. And this, again, as we've seen, this is usually called the spectral action, okay? And we've reviewed its construction already. I don't want to review the construction here. But I do want to say that in the paper, we kind of rebuild the construction using this D-rel systematically in all steps. And the reason that we do this is because we needed some kind of duality theorem for this, okay? So in the last, right, I'm going to go 2 minutes over time. I hope that's okay. In the last however many minutes, I want to state this duality theorem, and then I want to tell you what the restricted sheaves on bun G are, and then I'll stop, okay? And so we rebuild this. And also prove the following. There's sort of 4 different ways you can state this duality theorem. I'll state the most concrete one, which is the one we actually use. This is that for all compact sheaves on bun G and all perfect complexes on the stack of L parameters. So you might wonder what happens if I apply Bernstein-Zelinsky duality to this sheaf where I take A and act on it spectrally by F. This is still going to be a compact sheaf. And turns out this is, I'll use my preferred notation, but this is something kind of down to earth. It's the same as taking the BZ dual of A itself and acting on it by the Grothendieck-Serre duality of F, but then twisted by the Chevalley involution. So you could also write this more concretely as like C upper star, and then F is perfect, and it turns out that here Grothendieck-Serre duality is just naive duality on perfect complexes, okay? And so this is some duality for the spectral action. And the importance of this will become clear in the 5th lecture. This is also an ingredient in the analysis of T-psi. Okay, questions about this statement? Again, there's sort of 4 variants you can make on this statement, and this is the most down-to-earth one. So ask me maybe later if you're curious. And so finally, last thing and then I'll stop. What is D bun G restricted? This will also be important. And again, the answer turns out to be extremely down to earth. So definition, D bun G, fin, same psychology of what this should mean to you. So this is the subcategory generated under finite cones and shifts by things of the form IB lower shriek pi, where pi is a smooth, irreducible representation of GBF. So in some human sense, these have finite length in the strongest possible sense, okay? It's gotten from shriek extensions of irreps by finitely many steps, okay? This is a very, very thin subcategory, again, of D of bun G. And so let me just end with a proposition. So A is in D bun G fin. If and only if A is compact and ULA. So this is in parallel with what happened on the spectral side. Cofin was the stuff that was in CoQC and was admissible. Those conditions are in perfect parallel with being compact and ULA by design. But here, this is actually easier to prove. And 2, well, because things here are compact in particular, if I ind complete it, I still get a full subcategory. So ind completing D bun G fin, whatever that is, it will embed fully faithfully already into its container. And this is literally D bun G restricted. Okay? So in this context, again, now restricted has a more subtle meaning, right? Because I'm using the spectral action of this crazy O restricted thing to define it. But again, it's very concrete. It's the stuff that's obtained by colimits from Ereps on strata, and that's it. Okay, so I apologize I didn't have time to sketch the proofs of these last things, but I wanted you to see them explicitly because we're going to use all of them in the next steps. You should think that these 6 lectures are kind of like a roller coaster, where the first 3 we're going up to the top, okay, and now the 3rd one's over, and starting in the next lecture we're going to kind of shoot down the other side, okay? So that's what you have to look forward to. And I apologize for going over.